Hi. I hope you got a good weekend. I just noticed that half an hour ago there's a railway accident on the East Rail line, so some of you may be late, but we will start slowly. But today we will talk about the topic 2 about probability. Just quickly review. We spent 5 minutes to review a little bit about topic 1. By the way, just to remind you that you can try out the self-checking quiz, the blackboard, where there's multiple choice there. You can play around with that, and then you can check whether you understand or not. It's not credit bearing, so if time to do it, you don't have time, you don't have to do it. The answer is all there, so doesn't count anything, but just help you to check yourself that you know the material well, and it's not. If you want, you can attend, you can do it. If you don't need to. After the topic 2, we'll release assignment. That is the one that you have to submit. But currently, the multiple choice question are just for you, in case you want to check out whether you got it right or not. So as I said, let me very briefly review this guy, right? So in topic 1, we talk about descriptive statistics, right? Talk about mean, we talk about variance, we talk about kurtosis or self-skewness. They have all commonly used, and turn out they are actually closely related to the probability, the things we mentioned today. But before we do that, we will mention about probability. And I think I mentioned the very first class why we need to study probability is the fact that summarizing from the data is not sufficient, right? We not only want to know the data, but we want to use the data to draw a general conclusion for the stuff that we haven't seen from the data, right? For example, we are having the data up until now. We use it to talk about things in the future, right? Use it for business decision, right? We look at how people like our product, how much they're willing to pay in the past, right? To indicate how much they're willing to pay in the future, right? So future, we don't know yet, right? But we are going to make some assumption that the conclusion drawn from the historical data is going to work for the future. Or we are not able to look at every single individual we want to study, but we are only look at some part of it. We want to say what the conclusion we draw from data are going to be valid for the things we want to study, right? For example, if you want to know, say now the big thing is US election, right? Unless we ask all the people in the US, then you never know who they're going to support, right? But you can see most of the poll, they will only look at thousands or at most 10,000 people. How the conclusion drawn from this small subset of the population is going to hold for the real thing, right? That rely on probability. Okay, the probability actually tells us how to do it. And if you learn in the in the high school, right? Probability actually started from the gambling in the mathematics. Those people will try to consider gambling. Rolling a dice, tossing a coin, and all basic things. So that is how we're going to deal with them, and then start with these definitions. And then the next topic we would talk about random variable, which is a simplification of the thing we want to study. Okay, but that would be something we talk about I think in early end of this month or October. But for this 2 weeks time, we talk about probability. Okay, and just to remind yourself that why we want to deal with this method object is because we want our conclusion drawn from some specific data going to hold, going to be true or going to be believable for general conclusion we want to do. Okay, so that is the idea we want to do that. Otherwise, you ask, I want to crunch number, the data, right? Why related probability at all? So that would be the key. Okay, so let's start with the standard definition of probability. We start with random experiment. It's the object we talk about probability. Random experiment is something that an object that we know something is going to occur, okay, and we know what might occur, but we don't know exactly which one will occur, okay. That means that there's no surprise to you this outcome actually occur, but this actually happen is surprise you, right? For example, you toss a coin, okay, it's either head or tail, right? One side would O, right? It doesn't happen to be a magic, you toss a coin, disappear. Okay? If vanish the thin air, then it's not the thing. We know it's either head or tail, right? Or you roll a die, okay? Once you roll it, okay, it's one of the 6 faces. It's not come out rapid. Okay, it's not magic. So it's something that you know one of the outcome to be true. You just don't, you may be surprised by actual outcome you observe, but you're never surprised by this outcome is possible. Okay, that's called random experiment. Of course, that means that with some limitation, right? We cannot model the things that are with no idea, right? We only can model the things we have rough idea what are all possible outcomes. Okay. The second is outcome. As I said, outcome is the things that come out from experiment. All right. Example is toss a coin. Head is an outcome. Tail is an outcome. Ring a die of 6 faces. Number 1 up to 6 is also all the outcomes, right? Each of them is an outcome there. Okay. And the next is slightly complicated. You call event, which I think you also learned in the high school as well. Is collection of outcome. Is some outcome together we call event. For example, if you roll a die, right? An event of even number is consists of outcomes of 2, 4, and 6, right? An event of odd number consists of 3 outcomes is 1, 3, and 5. An event of large number may be considered as an event that consists of outcomes for 4, 5, and 6, right? An event of small number can be considered as a collection of outcomes of 1, 2, and 3, okay? So a bunch of outcomes together, bundling together is called an event, okay? And we'll call the event is true if any one of the outcome is true, right? We'll call the event even number if something happened if either 2 or 4 or 6 had happened, right? So that is how we define event, okay? Lastly speaking, we have a final terminology is a sample space, okay? Sample space is the event that consists of all possible outcomes, right? So basically, by writing probability in this way, we exactly know what are possible things, right? That's called the sample space, right? We have a complete description of what might happen. Why we define it this way is because people talk about gamble, right? When you gamble, you must know what are possible, and you bet on some outcome might happen, some outcome might not, right? So that is why we have that, right? Probably you may ask, is it a good theory, but so far this is the best we have, at least when we talk about statistics, okay? And at least now is sufficient for the purpose. So if you roll a die, the sample space is 1, 2, 3, 4, 5, 6. Toss a coin will be head or tail, right? With the completely the whole description. Okay. Once we have these 4 terms, just remind yourself is random experiment, outcome, event, sample space. We can define the classical idea of probability. Okay. As we said at the beginning, why the probability is starting from gambling. Okay. And the thing that they would start to look at is what is a fair bet at the beginning, right? What would be how to assess probability of certain event would happen, and they decide a fair bet between 2 agents, right? And decide no one would win or lose in the long run. Okay, so probability is to quantify that, right? If we call a bet or coin is fair, right? A bet is fair, right? If it's equally likely, which is considered 1/2, right? And that's why we define probability will be if you repeat this random experiment many, many times, okay? And you count how many times you do it is the denominator, right? And how many outcome that favorable event as a numerator, right? And by construction, this fraction, this is a number, is a fraction between 0 to 1, right? And 0 is never happen. 1 always happen, right? Half is good likely, right? It's a nice number there. Of course, some of you may actually wonder, to you may be very natural, right? Because you start from high school, you learn is 0 to 1, right? That is something that's not something not very odd to you, not strange to you. But indeed, the beginning, actually, they don't talk about probability. Later, you see the odd ratio. This is something they start at the beginning. It's not limited to 0 to 1, but 0 to infinity. And later, people think, okay, this is a better idea of descriptive because 1 is always happening, right? Infinity is very hard to think. But odd ratio is still used in betting. In horse racing betting or in casino betting, odd ratio is still commonly used. But anyway, later we see. But so you can see this is come from science experiment idea, right? Just you think about probability, something can be repeated, so you can conduct experiment, right? So you keep doing that, you roll a die, or toss a coin, right? If the coin is fair, you can expect if you go for 1 million times, actually you can do it, right? 500,000 should be head, 500,000 should be tail, right? Roughly, of course, it's not the same, but approximately. Then we will just say this probability of head and tail will be 1/2, right? Then it's a fair, right? It's a fair coin, you will say, right? Because equally likely, right? Because maximum is 1, right? Half is midway, right? So the classical probability, of course, is very simple, right? But the restriction is being that you can repeat this random experiment, right? And potentially, it's not clear a lot of things can be repeated, right? For example, what's probability that tomorrow the stock price go up or down? Tomorrow only happen once. It can't happen again, right? So that is cannot be said, but can we say probability about tomorrow has a ring or what, right? That's we can see weather forecast, they have that, right? But what does that mean? This definition is about long-run frequency. So that's why this is called the frequency-less probability, right? And the way that we talk about something or judgment or conjecture, they call Bayesian style. But we'll not go into that to discuss the probability philosophically. You have to go to philosophy department, right? So we just use the standard idea of frequency-less approach. And indeed, the study we have throughout this class is the classical frequency-less approach. And if you like the Bayesian approach, that would be something you have to learn in grad school. But we learn some base rule to tell you some idea. At the end of this topic, we talk about some base rule. You understand what does the base mean, okay? A Bayesian probability. But this classical you learn in the undergrad, okay, or in the high school, which you can imagine that you can repeat, okay? It still rely on the physical world, okay? And later we'll define probability just by definition, without refer to the physical world, okay? And so far we are linking the probability to something we can do experiment on, okay? This is a classical definition. Now let's look at this, okay? If a die is fair, a 6-phase die, you have 6 outcomes, and each outcome is equally likely, okay? And if you have a even numbers, it's an event because 2, 4, 6, right? And odd number is 1, 3, 5 is an event, and L is 4, 5, 6 also event, right? The sample is 1 to 6 because this is all possible outcomes. And probability even, right, is you count how many of them, which is 4. How many outcome is 6? So it's 3 over 6. Probability of odd is just 3 over 6 again. Large is 3 over 6. Okay, and then you can simplify 3 over 6 is 1/2. So that is standard definition. Nothing very new. I think you know it. I mean, when you're in the high school, so there's nothing new here. And I don't know whether you draw the Venn diagram. This is a diagram usually to illustrate how these events are related, which we'll use very soon. Okay, and you can see the S is the whole sample space. Okay, it's a square, and the green circle consists of odd number event, which is 135. E is even is 246, and large is 456. Okay, and by construction, there's nothing in this all three circle intersect because there's nothing is even and odd and large. Okay. Okay. So now we're getting increasingly a little bit more complicated. Suppose you roll a die twice. Okay. You roll a die, look at number, and roll a die again, have a number. Okay. So then, because of you roll a die sequentially, not two dice at the same time. So 1, 2, and 2, 1 are different. Because 1, 2 means 1 and then 2, and 2, 1 means 2 and then 1, and they're different. Okay. So so the sample space is much more complicated. If you learn math, you actually will see this is 36 outcome because you can write a row of 1 to 6 and column to 6, and all the entries in the spreadsheet, right? If you think that's about spreadsheet, right? On the box of the matrix will be 36 numbers, right? 6 by 6, right? A 6 by 6 square. Each square will represent a one outcome there, right? And let's look at the event. Sum of two row is less than 4. Okay. Then this particular event consists of 3 outcomes. You have 1, 1, 1, 2, and 2, 1. You cannot have 2, 2 because 2, 2 is 4. Less than 4, right? Less than is not doesn't include the equal to. So only 3 outcomes. And 3 over 36, right? It's a fair die. That's the probability. It's 1 over 12. Okay. So this is how you can do calculation. Okay. If you go to math departments, that department, they will have a lot of this kind of calculation, telling you different ways of doing probability. But since we're not in the math and stat department, we just leave it here. Okay, we're not going to challenge you for do the calculation, but just have the idea what's probability, right? It just to repeat the fraction where the denominator, if you keep doing this experiment, how many times you do it? Okay, you do a lot of time, and the numerator would be what? Would be you count the event that is favorable. So count the number of outcome, the favorable event, right? Suppose you want this 2 dice that is less than 4, some of them, you just count 1, 1, 1, 2, and 2, 1, and 3 of them. 3 over 6. This is the idea. Okay. Now we are getting slightly more difficult, okay, because we will have what we call operation on event, operation of set. If you learn logic or physics in the logic gate, or you learn philosophy, the logic, there will be something there, the interset, union, and complement. But don't worry about that. Interset is just the English letter N, A-N-D-N. Union is just English letter OR. Okay, and this OR slightly the logic OR is slightly different from the standard English OR, because usually OR means either of them is true in English usually, but this OR in logic is also included. They both are true is also fine. A or B, if both A and B happen, is still true. Okay, slightly loosely speaking different. And complement means something is not. English means not. So when you see interset, it just and. Union just means or. Complement means not. The reason why I have to introduce it, because the standard terminology there, when you read the book or other text, then you have to know it. I mean, of course, I can use English, but this is how people define it. Okay. So let's see the idea, okay? Intersection. Why we do that? So I have one event A and one event B. I want to create a new event, which is interset, okay? And which often we use it. Say all the interset means N means that common event. That is similar to what you do, what we call the finding common factors, right? You have 2 numbers. You factorize it, find the common factor. It's like that idea, okay? So maybe example will suffix to describe it. So if you see the rolling a die again, 1 to 6. Your event even, which is 2, 4, 6. Event large is 4, 5, 6. Event odd is 1, 3, 5. Okay. I want to create new event, okay, which is E intersect large, even intersect large. So I want to look at outcome that are both even and large. What you left is 4 and 6. Okay. Why? Because 5 is not in even, 2 is not in large. So you drop there. You only look for common element there. Okay. And O and L, okay, look at every single element there. 1 is not there, 1 is not in large, 3 is not in large, 5 yes, right? Look at large, 4 is not in O, 6 is not in O. So only 5 is in both. Okay. Look at both. Okay. That is intersect. Okay. So basically, just like you have the two circle there, the Venn diagram like this is the one that is overlapping the two, right? So you have even is 2, 4, 6, and large will be 4, 5, 6, and the common element in the middle is 4 and 6. Okay. And you may ask why we need to do this. Later we will see that is how we define probability. Okay. That is called the axiomatic definition of probability. We have to start from this one. Okay. And union is just very similar to when you find the lowest common multiple, LCM. Okay. And you figure out all the outcome that is appear in either of the event. Okay. So look at the same example. You have E union L. You just pick whatever in the E and L. Okay. You don't need duplicate, because for the set notation, this is the notation of set, duplication has no meaning. Okay. You can just pick whatever there, just take out a duplicate. Okay. E union L is, you can check 1 by 1. 2 is here, just put it there. Okay. 4 is here, just put it there. 6 is put it here. And 4 is already done. 6 already done. 5 is not, so just include them. You're done. Okay. And O union L, we just do the same. Pick up everything there, remove the duplicate, and that's it. Okay. That is O union. Okay. So that's basically everything there. Okay. Last is called complement. As I said, it's a not, N-O-T, not. That's not. Okay. So if I have S, okay, and I have even number, okay, the complement of the even number is not, that means not even number. Actually, by construction, you know, not even number actually means odd number, right? Because number is either even or odd in for the die, right? So that's why this is same as odd, right? And similarly, is complement of odd is actually even, right? So how to do it? Let me do it once, right? Complement means you go to say how to find this. Okay. How do you do that? You just look at this and cross out the thing in the even. That's a complement. Okay. And you can do the same for large. You cross out things of large in the sample space. Then what you left is the complement there. Okay. I think you have learned that in the high school already, but I just I don't think you learned it formally, right? But that's how, I mean, immediately we explain why we need this. Okay. So not means it's a E that's outside E, right? So let me immediately explain why we need that after we define certain thing. Okay. So first, after we define what is intersect, what is complement, what is a union, free definition, we can define one is very useful idea. It's called mutually exclusive. Okay. Mutually exclusive is if A happen, B cannot happen. If B happen, A can happen. So if one is true, the other must be not true. But it is possible that both are false. Only thing you rule out is it can't be both are true. Okay. So in that case here is London and New York are mutually exclusive. If you are New York, it cannot be London. If you're London, it cannot be New York. You cannot in both London and New York at the same time. But you can be in Los Angeles, then that none of them is true. Okay. So by construction, that means that there's no particular outcome that is in the intercept. So there's no way that both of them are true. Okay. This means 0 and a cross is called empty. There's nothing there. Just the notation used in all the probability textbooks. So none of the notation invented by me. Just if in case you read it, then I just leave it there. Okay. Another event is called exhaustive. Exhaustive means by English is exhaust is used up, right? Exhaust means that if an event is exhaustive, then it must be true. The probability of that is 1, or it means that it equal to the union of them equal to sample space, right? And right, I think it's right that everyone is in the universe, right? No one escaped from that by construction, right? Either right, I think there's one thing that is always common, but probably those people not in Hong Kong will not know. I think there's one famous commentator on soccer, football, not the American one, but the UK one, the soccer. And when they have penalty kick, I don't know penalty kick, right? Penalty kick and no penalty kick, right? And they said before the penalty kick, I mean, they say something happened, right? Then the commentator will say something and say, okay, now is penalty kick. There are 2 possibilities. Either it's in or not in. I mean, they say in the rubbish word, right? But that is how they said it, right? And then say, okay, the modern soccer, the ball is round, so one side may be win, one side may lose, right? We know it, right? Because all are nonsense. But nonsense means exhaustive, right? It's either this or that, right? And also, you look at the old Hong Kong drama, right? There was a woman, many of the time, this woman who is sometimes confused whether her boyfriend loves her, and he will pick a flower with a lot of petals. He will press a petal. He loves me. He don't. He doesn't. He do, and so on and so forth. At the end, it will turn out that he's crying, but you know the outcome. But that is it, right? Because exhaustive, right? He says whether he loves her or he doesn't, and so on and so forth, right? It's exhaustive. Okay. So exhaustive means that the union is the sample space. Okay. The final one. Now after this we'll define probability. Okay. We'll then define probability without talking about the real world, right? Because when you learn the probability in your high school, we rely on experiment. Now we want to move away experiment, so we have to find out this one. It's called partition. Partition is a rather simple concept. Is you do it tomorrow. Why? What's tomorrow? What's going to happen tomorrow? Tomorrow is Mid-Autumn Festival. We're going to eat mooncake. What do you do? I don't think you pack in the whole mooncake to your mouth. You want to cut it, right? Unless you're a big mouth, but usually the mooncake is so large, no one can put the whole mooncake in the mouth unless you're a small mini one. But you're going to do is you cut mooncake into small different parts, right? And actually that's called partition. Means that you cut into multiple parts and none of them overlap, and all parts add together is the whole thing. Okay, which means that if you combine mutually exclusive and exhaustive, then it's partition, right? Because none of the parts overlap, right? You cut everything all joined together, it's the whole mooncake. Okay, so that's by definition. Okay, it's exhaustive and mutually exclusive, right? You cut every part, none of the parts are related to each other, and all about the part is the whole mooncake. Okay, so that's the idea. The graph is the sample space is S. You cut to n different parts, and none of the parts are going to intersect with each other, and union all the parts is the sample space. So that's in 0 empty intersect, and union of them is the sample space. Okay. Now we are ready to define. Before we do that with example, okay, we have again a die 1 up to 6, right? And even number, odd number, okay. P is a new thing. P is a prime number, okay. And B is the big even number. I call B. I don't call B, but anyway, B. Okay. So first is odd number and big even number are mutually exclusive, right? Because it cannot be both true. The interset is empty. Second is the collective exhaustive is OPB because either O or P or B would be true. Cannot be all false, right? So you can see the mutual exclusive cannot be both true, and collective exhaustive is one of them must be true, right? So cannot be all false. That means, right? Because they are too extreme. Okay, and turn out that the even and odd will be a partition, right? Because it's either E or O must be one of them is true, cannot be both, right? And that is the idea. Okay. Now we will define probability, and this probability is based on math, nothing but with the real world. And this is the axiom definition. It's come from a Russian mathematician, okay, in 1900. And if you learn the frequency list, the one that you define, the probability, okay, we have someone, okay, I hope that's okay. I mean, he's checking everything. Maybe someone violate national security law in the chat, whatever. And this definition, actually, the mathematician take 300 years to do it, right? Because the frequency list idea, ratio, is actually defined in 1600, right? But Benoni or Fermat, those people, like long time back before Industrial Revolution, right? It's right before World War I, or around that time, right? They have this. They define, mathematicians figure out how to define probability without talking about real world, just math, just numbers, just use the terminology we use. Just use union, interset, adding and subtracting, that become probability. That has no real world content. Okay, of course, when we learn something that's no real content, we can learn a lot of deep thing, but we still need to connect to the real world, right? Because we take out the link, but at the end we want to link to the real world. Okay, that we will do in the next section, right? This is about probability, but we talk random variable that will connect to the real world. So we just take things from the real world, just from the math world. We learn a lot of things, and then go back to the real world. Okay, and by doing this abstraction, like physics, then you can go deeper without relying on whether we can do this experiment or not, right? Because now we don't have to worry about the conflict between whether things can be repeated or not. Can we know the sample space or not? We don't need to know. Okay, we just define it. This is what we know, and that's it. Okay, so that's our trouble. So we start with 3 assumptions. It's very simple. Turn out to be very nice. It's 3 assumptions there. The first one, nothing deep here. It just say we want to say give me an event in a sample space. Okay, the probability is just assign a number between 0 and 1. That's it. Nothing deep there. I think everyone can accept this as a measurement, right? So give me a sample space. I have some event. I just said this will give me either 0 to 1, right? Anything in between cannot give me a negative number, cannot give me more than 1, right? When people said the probability of this happen is 200%, of course, that was idiot, because probability by construction must be 0 to 1. You cannot say probability is -5 or -2. It means nothing, because by construction, by definition, we call probability. We know it must be 0 to 1. Okay, cannot say 120%. This is going to be true. No, it's either it must be 100%. Nothing more than 120. Nothing you can go beyond 1. You cannot go below 0. Okay, 0 means nothing. Cannot, never happen. Okay. Now the axiom 2 is also nothing deep there, but it just, we define it, the probability sample space is 1. Okay, actually that means that there's no way you can be surprised. This thing can happen. We know what might happen. Okay, what are the possible outcome there? Okay, but we're surprised this actually happened, but we're not surprised why this can be true. Okay, as I said, that's the magic idea, right? You toss a coin, it must head or tail. It cannot vanish in the thin air, right? It's like either he loves me or he doesn't. It can't be he's an alien or he's a ghost. You cannot be like this, right? It can be either two outcome. Okay? You can't be he likes me and also he doesn't like me. Look, it can't be like this. Okay? It must be one of them. Okay? Now, finally, this one is slightly a little bit tricky. Okay, this is the most tricky one because the first two are nothing, right? Just like must be 0 to 1. We know everything. Everything must be 1. The last one is the most difficult part. Actually take mathematicians take them 300 years to solve this problem. It's actually the axiom 3 to come up with this idea. Okay. So if we have an event that consists of mutually exclusive outcome, like Roy die, and event is 1, 2, 3, right? 1 and 2 and 3 are mutually exclusive, right? And they are no overlap, right? It's either outcome cannot be true at the same time. And then the probability of that event will be sum of all the outcomes. Okay? The part is sum of its whole, right? The probability of even number is probability of 2, probability 4, and probability 6. For 3 of them add together must be same as probability of even number. Okay? Probability odd number is same as sum of 3 parts. 1, 3, and 5. Because odd number consists of 1, 3, and 5. It must be you look at its part probability 1, probability 3, probability 5, add together must be same as probability of odd number. That is very natural. Is it? Right? Is it? I think it's very natural. Right? The probability of something, right? You partition it, you cut it into several pieces, right? You look at one by one, add them up, right? The whole must be part of sum of all the parts, right? I think there is nothing deep here, right? But you will ask, why mathematicians take 300 years to solve this problem? The reason is, with mathematics, okay? For those who does M.Phil or advanced math, the reason is when n is finite, that's no problem. Everyone will agree. When n is infinite, you add infinite part, how to add them up? That's a very deep problem there. Okay, that require a lot of limit kind of idea there. Again, how to count infinite subset of empty thing. It is very complicated. But we're not going to the difficult problem there. Okay, as long as everything is discrete or finite, then actually there's nothing new here. But we will just avoid the problem. We will assume that calculus would work. Everything looks nice. That will, if we want to study more, that will be go to math or stat department. Okay. But this thing you can see this 3 axiom. Okay. First is probability must be 0 to 1. Probability of sample space must be 1. Probability of its whole must be sum of all its parts. Okay. This 3 axiom define all possible probability rules, which now we don't actually rely on anything about real world. Okay. You just tell me, as long as you assign probability according to this 3 axiom, 3 assumption, axiom means assumption, okay, then that's probability, and we can do all of the calculation. Okay, and that is what you learn. Okay, and just example before we go to break. Okay, now we have how does it help? Because now we can go by assumption without relying on experiment. Okay, start from this one. We have a total coin, roll a die of 1 to 6. Okay, axiom 2 tells us if this is sample space, this probability of the S must be 1. Fair enough. Second thing is axiom 3 tells us, right? The sum, the whole must be sum of its all parts. So probability of sample space must be probability of 1, 2, 3, 4, 5, 6, because they are mutually exclusive, right? And then now here comes the difficult part, is we make assumption here. Okay, you can make an assumption, but we make assumption the die is fair. That means that probability 1 equal to 2, 3, 4, 5, 6 is equal to the same. Okay, but the left-hand side is 1. Sum of the 6, the same thing, means 1/6. That is how you derive 1/6. We do not make any assumption about rolling this die 100 times. There's no ratio there, no fraction here. We just make assumption here. The assumption is every outcome the same. Then you get this one. Of course, you can make assumption like this die is unfair. Probability 1 is twice likely as 2, 3, 4, 5, and 6. Then you can do the same. You can derive the probability, right? So we don't really need anything just by assumption, right? Just we forget about the real world. We don't need to say when we are calculate probability, we don't really need to repeat the experiment. As long as we make assumption there, then we're fine. Okay. And how to make this assumption? From physics, from business world, from theory, from other things, we know how to derive those assumptions there, then we can do prediction, right? Otherwise, how can we do probability, right? Other than toss and coin and roll a die, right? How can we predict the weather? Because weather never repeats itself, right? From some physics, we know this condition to that, okay, then we can do something, make some assumption there, right? Or the weather forecast is based on very complicated model that will tell us which outcome more likely, but that is coming from this kind of idea, okay? And probably even, it's just 2 plus 4 plus 6, and we say it's fair die, each one is 1/6, so it's 3/6, it's 1/2. So we can see we don't need to run the experiment. We can make assumption, and the axiom will tell us how to derive probability. That means that we take probability just by itself without, as long as it's a free axiom, we don't need the real world. Okay, of course, the assumption is come from real world, but we don't need the real world to be there to do our calculation. Okay, that is very important for business, right? Because say you do a business survey, you only do in Hong Kong or some city in China or some city in US, right? You want to apply to other international cities, say London, right? And then maybe there's some demographic changes, you make some adjustment, but you want what we learn from one city to be translated or transferred to other city. Then that is the idea. Why it work? Why we don't have to do the survey in the UK or London? Because of we make some assumption here and there, and then that's we can make an educated guess. Okay. So I think it's time to break of 10 minutes. As I said, we will do a U reply in case you want to say something, or you tell me whether I'm going too fast or too slow, let me know. I walk around to see if you have any question. Well, when you have you able to well, I also wonder how much this knowledge they expect. Yeah, it's kind of about the process. Yeah, they don't do it with the but I don't know how useful it is for that. But I think how I'm excited. So I appreciate your work. Come back. So I think we have break. It's over, unfortunately. Always we want more break than is available here, and why? It's not working. Why? Let's see. Report. Let's see the result. First is understanding the field probability. So I hope for the first half of this class, you know probability, how we define them without relying on experiment. And we show you how logically you would say roll a die. So roll a die is 1/6. That come from these three axioms that we have. Okay. And oh, I'm sorry you can't get the train. So you want to play the mooncake and eat the lantern. Okay. Can you show some example? Oh, actually, that's what we're doing. And if you want to do more probability, then you will go to the stat department. So what we do is give you a high-level understanding of probability and tell you some rules that you do calculation. And later, at the end of this class, not this, maybe not Wednesday, next week, we'll talk about Bayes rule, which is the most useful thing in terms of probability. What Bayes rule is later I'll describe is how you update your probability. What does that mean is, like the finance idea, right? You don't know what's the value of the stock. Okay, like option pricing, it can be worth $1 or worthless. Okay, and at the end of the day, when things go develop, right, you keep updating until you learn more about the real world, right? So that is the Bayes rule. That is the most important. It's information update. You learn information, you learn new thing, right? It's like a boy and a girl, right? In a relationship, right? They learn more and know more. They learn more whether they love each other, right? The right type, the true type, right? And then they maybe engage and get married, so on and so forth, right? Just like a learning process is modeled by Bayes rule, and turn out to be, if you learn, right, that is how the AlphaGo is being done, right? You learn how they train the AlphaGo, right? Is the original AlphaGo is by training by the human textbook, right? And then they calculate probability and then decide which location has the highest probability of winning, right? And after that, the advanced version of AlphaGo is two machines play each other, right? And then they keep playing millions of the game, and they learn which location is the most likely to win. How do they learn which one? Is called Bayes updating. That's what we learn. I think it's next Monday, right? Then we'll learn how to do that. And many of them of the artificial intelligence or machine learning are based on the Bayesian style of learning, because Bayesian learning. It's the way that we discuss next Monday. But of course, there's a new thing that's non-Bayesian learning, but there'll be similar thing. There's some learning process there. So basically, it's just like how we learn. How open is final? As many as you want, as long as the paper. Okay, as long as paper, you can bring as tall as you, I guess, as long as you can carry. But do remember, you can't share. That's the only thing. Okay, you can bring, and also you bring your calculator up. That's the thing. Bring your calculator. Cell phone is no, because of the communication. You bring your standard calculator without internet function. That's really fine. The reason is not because of I worry about your calculator have some cheat sheet, because you can bring infinite cheat sheet. The problem is communication. If the phone then maybe Bluetooth, then it can be dangerous. And then if there's someone cheat, then you have to take the exam again, right? There's a case like this. So I don't want it to happen, right? So just, I know it's not environmental friendly, but we have to print that out. Sorry about that. Actually, I don't mind. I mean, to me, what's the difference? I'm not doing anything, right? Just, right? Seriously, you're hungry? Okay, I'm sorry about that, but you should try to eat before you come. Oh, yes. Someone dropped into the Israel line. So, so please, if you want to suicide, please contact for help. So, someone asked me, am I microphone student? Microphone is one professor who just retired, full professor. Was undergrad, he did taught me about the one class, Managerial Economics. 3000 D is 3000 class, but that is the only class I took from him. But technically, yes. Yeah. If you want to commit suicide, yeah, shouldn't do that, because you also disrupt others. But anyway, please don't suicide, right? If you there's a lot of hotline you can call. There are a lot of good things in the world, right? Of course, not everything is nice, but there are many good things in the world, right? And CHK is a nice campus, right? If you feel confused, you don't happy, just walk around the campus, make you happier. Okay. Yeah, I'm sleepy. Yes. Again, recommendation, coffee is your friend. Oh, I'm pretty surprised people think it's a Friday. Is it the typhoon effect that long you want holiday that much? But we have holiday on Wednesday, right? So I hope that would be fine. Yep, that is a good one. It's sunny, cloudy, and slightly windy. So that's a good. No, probability cannot be 0 to infinity. Probability must be 0 to 1. Okay, later learn odd ratio is 0 to infinity. That is, we'll talk about that. If not today, will be next Monday. But probability must be 0 to 1. That's axiom 1. Must be any event must be 0 to 1. Axiom 2 said the sample space is 1. The axiom 3 said probability of a whole is sum of the probability of all the parts is equal to. Yeah, because, well, for those who feel axiom are difficult to understand, it is right to do so. Remember, it took 300 years for smart people, mathematicians, to really come up with the axioms. Okay, so it's not that easy. But I want to say the axioms actually fit our intuition of why you roll a dice 1/6 without relying on running experiment. Okay, if you can get it, it's okay. If you don't get it, you just apply the rule, that's fine. I mean, the background understanding, I try to convey the message, but if you don't really fully get it, it's okay. Okay, you don't have to fully understand a thing before you use it. That's business world, right? You never understand how a computer works, how the chips work before you can use computer. You can still use it. You just need to know basis, right? You don't really need to know every single thing to work it. Yeah, that's right. Of course, the three axiom also have axiom 1 and 2, right? Axiom 1 and 2 said probability must be between 0 and 1, sample space is 1. Okay. Probability whether a boy likes a girl. Yes. That is not, you cannot run experiment, right? Say there's a one girl there, whether she likes me or not. You cannot run experiment unless you go to multiple universe and ask her, and then can calculate the ratio. But given our technology, we cannot do that, right? You can assume it's equally likely that it's 1/2, right? You can make some assumption, or you can look at the sign and then do something in a checklist, right? Whether how many minutes you look at me, okay, right? Something like that, right? So on and so forth, right? You can do something, but that's the definition. Summation, partition, yeah, that's good. Yeah. So I have one person who really hates me. Oh, and don't like the speed of the class. Whether I'm too fast, or maybe he thinks it's too slow. I don't know. Now, so you can see whether the one that is a good exercise of to see this data, right? The data here say there's a one guy, he said, or one boy or girl said the speed is inappropriate, is disagree, right? So I don't know whether fast or slow. How can I check? So come from the other question, question 6. You can easily follow the lecture, okay? And I assume the same guy, assumption, the same guy, okay? And this exactly guy, he think I'm too fast, okay? And I just want to emphasize that I'm doing the first half, it is more philosophical, okay? The definition. If you not really comfortable with that, it's okay. But I have to give this definition because you will come up with the conflict between the Bayesian Bayes rule later if you keep talk about frequency list, because something you can't really repeat the Bayes rule. Okay? Because for the, say, for example, for option pricing or asset pricing, right? The stop price is either, in the future, is either $1 or $0, right? You just don't know. So there's no experiment to look at. So the classical assumption of the probability doesn't work. There's no experiment, right? Tomorrow is $1 or 0. You just don't know, but there's no uncertainty here. You just don't know. You can't say probability. But if you rely on axiomatic definition, you don't have to rely on this experiment. You just say there's some axiom, as long as your system is consistent with all the axioms, they're done. So there's no need to take side on what's probability. No. Probability is just something we give some number from 0 to 1 we give to some event. That's it. So that is the idea. Okay. Figure. Yeah, please come with the good one to share because it's a good thing to do. So there is a comment saying that tomorrow, which is the exact day of Mid-Autumn Festival, and one of you have to attend the ACCT 2111. I don't know what's that. It's a financial accounting. Oh, then I hope everyone have a happy Mid-Autumn. Okay. To be honest, the only class that I run away in college is ACT 2111. Yeah, I also find I want to attend the class and I always attend, and then in the middle of class I just sleep. I just sleep. I mean, I don't know why. I mean, I just sleep. Regardless of how much coffee I drink, I just go there and just sleep. I mean, the T entry and then debit credit, I always sleep. I mean, anyway, hope you don't suffer too much from that class if you don't like. So someone said, I don't know how to translate. Just forgive me, I don't translate. Let's see what is it about. I can copy and paste. Copy. I can't place. I try once more. If I can't do it, then that's okay. I really can't. Copy. Okay. Let's see what's that. Oh, so one good thing is the High Hotel. They have 2 dish discount. $88 have a nice dish. Can you see? Nice pizza, not including this man, but some of the pizza there is $88. Maybe you can try. Okay. Oh, I think you can try. But okay. Oh, sorry for that. Monday blue. But we have Tuesday holiday. So I think you said it's kind of good. Oh, just about Monday blue. I do have a paper, academic paper about finance. Do talk about the stock price actually go up on Friday because of holiday. And there are a lot of paper talk about Monday blue. The stock price usually tend to be lower on Monday as well. But that is not my research. But the Friday thing is I actually figured that out as well. But anyway, people are responsive to holiday things. So I hope my class on Monday, okay, not that bad if you have other class on this morning. But if this is the first class of the week for you, I'm sorry about that. Hope you will be fine. Not too bad. Okay. So let's continue. As I said, axiom 3 seems nothing deep. But the problem is when this goes to infinity, is a union of infinite set, and how this convert to that is very problematic. And if you ever learn mathematics, actually most of the problem come from taking infinity. And how to think infinity is a very deep problem. A lot of counterintuitive thing. And actually, if you know those several mathematicians actually study infinity, go to the mental hospital. The first few guys, the Cantor, or those kind of people. But it's not easy. I mean, don't think too much about infinity. Maybe you get depressed. Okay, so as just to remind you, right? The classical definition of probability rely on an experiment. You can repeat something that's really the real world. But axiomatic definition doesn't rely on the real world. As long as the probability thing you assign satisfy the three assumptions, then you're done. Okay. And how to fill up those things is by assumption. Okay. Now, and these three assumptions actually give us a lot of things. Okay. The first thing is the complement rule. Complement rule means if you want to calculate probability A, you can just subtract 1 from its complement and you're done. Okay, why? Because A and its complement is a partition, right? It's mutually exclusive, exhaustive, right? By axiom 1, A and A complement is sample space. By axiom 2, sample space is 1. So that is what you have. Okay, so this is a rule we got. Okay, and you probably ask why we do that. Okay, I'm not going to prove it because it's not math class, but I already said the proof already. Okay, it's not nothing new here. But why I do that? Okay, the thing we do that is often we do this calculation all the time. Okay, and later if you learn, you take this question to, we'll use this formula all the time throughout our course. It is complement rule. Later you will see. We want to calculate roll die probably less than 6. Okay, either we can calculate probability less than 6 is how many events we have is 1, 2, 3, 4, 5, right? But its complement is easier, only consists of 6, right? So instead of calculating 5 outcomes, we just need to know the 1 outcome, which is 6. And if even die, then it's 1 over 6. Then 1 minus 1, 6 is 5 over 6. Then our life easier, right? Why we do that? First, when we do that, we don't need to make any assumption on relatively, is it more likely between 1 to 5? Okay, as long as 6 is 1, 6, right? Then you're done, right? Maybe 1 is more likely than 2, it doesn't really matter. We don't need to make even, okay? As long as we know probability of 6, then we're done, right? Then we don't need to really have to care about how probability 1 may not be equal to probability 2, right? Maybe the same or maybe not, but we don't need that assumption, right? We just need to know this particular 6, and then we're done, right? So less assumption, but and calculation much easier, right? 1 minus. So just calculate. We don't know anything inside. We just know the outside. Then calculate this one. Then we're done. We don't need to count how many of them. Why? Because there's an example like this. If you want to calculate roll a die twice, if you want to know the probability less than 11, then your life is terrible because you have 36 outcomes, right? You count how many of them, but you count its complement less than 11. That means 11 or above, right? There's 11 or 12, and 12 is only 6 and 6. 11 is 5, 6 or 6, 5. Don't 3 outcome. So 3 over 6, 6, and 1 minus that, and you're done, right? So your life is much easier if you just know the complement and calculate complement and 1 minus. Okay, and there's a lot of time you do financial calculation. This is very often used because of a complicated object. It's very difficult to handle directly, but you go the other way around, much easier, right? Now, and we need to know some other rule. Okay, This is also a very interesting rule. Actually, this rule is a super useful rule. Okay, is one thing first is suppose these events are mutually exclusive, right? There's axiom 3 set. If A union B, right? There's A plus B. That is what the axiom 3 set, right? Axiom 3 means that, right? Whole is sum of parts as long as these parts are independent, right? Or mutually exclusive, right? To be exact, right? So, and what we have more is what happens if they're mutually exclusive? Okay? And we need to subtract the idea that they're same time. Okay? This is the addition rule. Okay? So the union is sum of them minus the intercept. Okay? Or intercept is sum of them minus the union because you just swap the most left and most right. Right? So let's repeat this statement, right? The union is sum of its part minus the intercept. Right? And you may ask why. Okay? The proof, I'm not going to do it, but I will do the kindergarten style explanation. Okay? How to do the kindergarten style explanation? Let me draw. I think it's good to draw a picture. Then I think you will appreciate that. Okay? So blue is A. The red is B. Okay? And what happened is inside guy. This guy is what? This inside guy is A intercept B. Right? And the green guy, right? Or I draw it this way. It's a heart-shaped stuff. Is A union B. Okay. So kindergarten will tell you the following: green, area green, will be area red plus area blue minus the sector orange. Why? Because orange overlap, you duplicate. So blue plus red minus orange is green. Kindergarten, right? Is that clear? That's it. That's the proof. All right? The union, the green one, is a blue, red, minus orange. Okay? Of course, if you want to prove it math, then it will be a little bit more complicated. But that is it. That's the idea. Okay? Red, blue, minus orange, green. So let me illustrate this example. Okay? And those of you are still worried about the math here. Okay? The one I showed you is the maximum math that is allowed in my class. Okay? So I'm showing the upper bound, that is what is possible being asked, right? Of course, the assignment will be similar. Okay? Of course, exam will be easier, but the assignment is the maximum difficulty that you can imagine. Okay? So, but if you're able to understand this, you should be able to do the assignment. I mean, that would be very similar. Okay? So if you roll a die once, okay, and asking what's the probability that is an even number or a number greater than 3, okay? So let's define the event A is an even number, that is 2, 4, 6, and B is an even number, and event B is 4, 5, 6, okay? Greater than 3 is 4, 5, 6, and A and B. So the question is, A and B is A intercept B is 4 and 6, right? The question being asked is or, so means A union B, okay? One thing you can do is do directly. Or means to take everything there, right? A is 2, 4, 6, B is 4, 5, 6. The union, just take everything there. Whatever you have is put there. And there's a 4 of them out of 6 is 2/3. Done, right? This is easy, you can do it, but sometimes this guy can be complicated. So how do we do it? Is we do it, remember, blue plus red minus orange is green. Okay? What is red? Red is A, probably A is 3/6 because 3 outcome, right? And blue is also 3 outcome, is 3/6. And A intercept B intercept is 2 outcome, 2/6, right? So we just blue, red minus orange is green. Done. 2/3. Okay? So just to demonstrate how you can do it. Okay? How you relate intercept or the union. Of course, for you, you may still a little bit puzzle for those who are not mathematically inclined people, because you may say, okay, this is a number, it's confused. Yeah. But I recommend you go home and take a look again. You do the assignment, then you will know. I mean, it's not easy. Like take all the math class, unless you're genius, you can understand instantly. But most of the time, you just take time slowly, do the example, do the exercise, understand. I mean, except the genius, you would just take time to fully understand what's going on. Okay, it's not instant. Okay, so this is the often you see it's called the contingency table. We learned first class. This is a two-way contingency table. Usually that's what the data you have. You have in the class you have a male and female. In total 80 person, right? Half of them are male, half of them are female, 40-40. Right? And then you have pass and fail. Only 35 people pass, 45 not fail. And you have some decomposition, right? For example, when we say 15 is 15 students who are pass and also male, right? And the red one means there are 20 female students actually pass, right? Remember, these are the intercept n, right? Because in this square means both of them are true. Okay, so this table tells you the intercept. Okay, so now what we learn, what we want is we want OR. Okay, first question is we want to know, suppose we randomly draw a student, how likely that he's a male or he passed exam, right? If n, that's easy. And we just 15/80, then we're done, right? But we're OR, so we have to do the rule, right? What we do is we have the red circle, blue circle minus the orange. That is the green. Carry the red, male, half of them is male because 40/80. Right? You randomly pick up a guy or girl, whether it's pass or fail, it's 35/80. Right? And men and pass, as I said, is 15/80. That's the table gives you. Then OR will be just red plus blue minus orange is green. That's it, right? And of course, the other way around is what is male or pass? Male or pass is just basically, you can look at this, it's just either male or pass. Just add up all the orange, right, over 80. So the same. So this illustrate how you can do that. Okay, there is and or and on the table. Okay, I do it because this textbook tells you, and then if I don't tell you, you read the textbook, then you're confused. It's not absolutely necessary, but this is something that you can read from the table all the time. Okay. Next is the rule we call the total property rule. Okay. And this is the rule that is same as the decomposition rule. Even A, okay, can be sum of two parts, A with B and A without B. Okay. So this is like the probability that the boy don't love the girl, right? The boy don't love the girl, and B maybe have an affairs, and then don't have no affairs, right? You don't love her, maybe there are two possible with affair, no affair, right? Why you do that? Actually, this is very commonly used in calculation, in mathematics. Is you want to decompose it, the future into two scenarios, and then this is how you do the calculation. Probability of this happen under two different scenarios, and under these two scenarios that you can know how to do it. Okay. For example, you want to know A is probability of the stock price goes up. Say, it's very difficult to calculate that. But if I tell you B is the event that the stock is a nice stock, right? It's a good stock. B complement means the stock is a lousy stock, right? If a good stock, then you can say probability go up has some very likely, right? If lousy stock, then will be very unlikely to go up. Then you can do this decomposition, then you can easily calculate things. So instead of calculate one thing, you decompose it in different scenario and do the calculation. So that is later we learn next week. This is the thing we do. Is we'll draw a tree and decompose it in different scenario, and this is the rule. Okay. But the idea why this is true, again, I will do the kindergarten proof. Now kindergarten hymn comes in. Kindergarten here, kindergarten there. This A, the green circle. Okay. Now we have another circle. Maybe I use the red one, is better, right? Because that's how I do that. The blue circle is A. And a reference B. Okay. So the blue circle, the blue circle can be decomposed in two parts. One is the orange part. What is orange part? Orange part is A intersect B complement, because outside B is B complement. And you have the green part, which is the vertical line here. What's the blue-green part here? The green part is A intersect B, right? So blue circle is the orange area plus a green area, right? Kindergarten proof, right? Right? So if a mooncake, you take a bite, right? The whole mooncake will be the front left and the thing in your mouth. Add together, it's a whole mooncake. That's it, right? Simple. So that is called the total probability rule. I hope that is not something terribly complicated, right? I think you learned it in kindergarten, right? The one A is the A with V, A with B. That's it. So this is the case, right? A and A with B and B without B. So in general, you can divide A into many small parts. Then you can complement that, then we'll be fine. Same idea. So I would like to end our class with this application called odd ratio, as I mentioned beginning, because this is exactly the probability how before the probability being invented. That's how people quantify the uncertainty in the world. It's called odd ratio. Okay. So in the old days, it's very difficult to talk about sample space or what, right? But people can say how likely A would happen is to compare how likely A would not happen. You calculate the ratio, right? If ratio is 1 to 1, then that's fair, right? So odd ratio is 1 means equal likely, right? Because there's a same number of ways that A and A not happening. So that is the ratio A over A complement, right? So that's the definition, right? This definition. And this can go from 0 to infinity, right? If probability A is 0, this ratio is 0, right? 0 still means 0. If probability A is 1, then this go to infinity, or as large as you want, right? 1 over 1 minus 1 is 1 over 0. 1 0 is very likely this could expand, explode, right? So basically in the old days, right, when people talk about odd ratio, is come from 0 to infinity. But it's very hard to say the odd ratio is 999999999. What does that mean? But right, so it's 0 to 1. Okay, and sometimes odd ratio have two ideas, in favor or against, but it just flip. So to make our mind not blow, we would stick with the first definition. If you do the second one, that's your mind explode, right? So just, I mean, already you have so many stuff to remember. So just don't make your mind crazy. Okay, just do the first one, because the first one actually fit the probability definition, right? You just from 0 to 1 becomes 0 to infinity. Okay, and why we care about this? Because this is closely correspond to the odd ratio in the casino. Okay, the probability is 0 to 1, but now from 0 to infinity. So this is how you match. When you say probability 1/2, the odd ratio is 1. When 0 is 0, this is the nonlinear mapping. Say, with the odd ratio in the old days, then we can talk about probability. But odd ratio is very hard to understand. So now the finally is the how we talk about the odd ratio in the casino, okay, or the gambling industry. So we talk about betting. 4 to 1 odd ratio means you bet $1, say particular team wins. If the winner get $4. Okay, that's odd ratio. That's you quote. This is the quote you get. You go to casino, you go to betting. Okay. So if you win $4. If you lose $1. Okay. And what do you mean by fair bet? Fair bet means that if you keep betting the same thing, you don't win or lose, right? It's break even. That's called the fair, right? Just like odd ratio. If you toss a coin, the coin is fair. It's 1 to 1. Then you win $1. You lose $1, right? So it would be a fair, right? So is the odd ratio against the outcome. Okay, it's reverse of the odd ratio we mentioned. It's called fair bet. Okay, why? Let's look at this. Okay, this is the last example we have. Then we're done. Okay, so roll a die, fair die once. What's the odd ratio? You get 6. Okay, definition itself minus its complement. 1 over 6 minus 1 over 6 is what? 1 to 5. Okay, if you bet this for $1, you win. If you win, you get $5. You lose $1. Then it's a fair bet. Okay, and because why? Because in 1 cycle time you lose $1. In 1 cycle time you win $1. In 5 cycle time you lose $1. Right? So if you win $5, then you cancel out. Right? And why we would want to mention this is because in many betting situation in the world, right, you can back out people probability prediction. Right? Suppose I want to bet how likely a US candidate wins using the betting market. How can I bet that out? Look at the odd ratio, post online. Okay, people keep betting. Okay, and then you can back out from the market probability how the market in aggregate think who is going to win, who is going to lose. Okay, actually, same thing can be done by option market or future market. Look at the temperature, look at weather, look at oil price. You can go back, look at how the market reflect people think about the future. Okay, and this can get a lot of probability there. Right? So the odd ratio actually reflecting probability, of course, only if the casino is fair, but casino is pretty much competitive. So more or less that would be right, because the casino only earn a very little margin. Okay, in terms of probability, only they can make money because of the last volume of the trade. but the ratio, the bet the odds they offer is more or less very competitive. Okay, so I hope I'm done with the probability. I mean, this particular class is very theory. So if you don't get anything, it's okay. I mean, I'm not particularly asked this thing, but to give you the idea what's probability. And after next week, next Monday, the one that you learn how to operate base is the most important thing. Other than that, then should be okay. So I learned a lot today, but I hope you're still okay. Stay safe and don't eat too much for the mooncake. I'll see you next week. Because we don't have class on Wednesday, okay? Wednesday's holiday. I stay around to answer any question you may have.